we talked about the program, and Neil and Stuart in particular asked me to come today and talk about, offer some reflection on the issue of building secure software or secure systems, and whatever that means, because it's not obvious perhaps. So first, I'd like to offer some observations based on, I suppose, something like about 15 years of experience that we've had with building secure systems. We first got involved in building such stuff some time ago, and then since then we've observed, I suppose, various trends in the industry and various things happening. Some good, some perhaps not so good, so I'd like to reflect on those things. I'd like to close really with a thought or a challenge, I suppose, about the future and how we may find ourselves building such systems in future, which will hopefully kind of lead into what Cyril's got to say later. So, 15 years ago, Altran Praxis, we'd been building safety-related systems for some time. Most of those systems were embedded, real-time, fault-tolerant, you know, all the good stuff that we thought we knew how to do. We'd been deploying so-called formal methods. We'd been using specification languages. We'd been using Spark to do formal implementation work. So, for example, we built an earlier generation air traffic control system for Alan's organisation. We went on to build a system called Solace in the mid-90s. Where we deployed a lot of formal methods and analysis. And then, quite out of the blue, unexpectedly, an opportunity came along for us to work on a very high-grade secure system that eventually became known as the Multos CA. This was built for an organisation called Mondex, who are part of the MasterCard organisation. And this job involved building what effectively is the root certificate authority for a smart card system. So it's basically a box that generates cryptographic material and keys and certificates and so on. And it was required at the time to be built to a very high standard of security. And we scratched our heads and thought, how can we do that? We're not so sure. But we looked at deploying the kind of approach we were using for safety-related systems in that security domain. And we were pleased to find that most of what we knew still worked. And that perhaps shouldn't be too much of a surprise to you. But a few key things were different. So I'd like to offer some reflection on what's different about secure systems, as well as what's the same and the kind of technology that we found we could reuse. So by way of some observations then, security in software and consumer devices and all sorts of stuff has become something of a hot topic in the last 5 to 10 years. You know, Ruston's here from Microsoft. How much has Microsoft invested in improving security properties, whatever they are, of operating systems and application software in the last decade? I mean, amazing resources have been deployed to tackle this problem. But it's not, you know, it's not just things like operating systems, all sorts of issues that we see around us. So things like operating systems, embedded systems are all around us and seem to be suddenly popping up. You read about them in the paper, oh, suddenly this system's been hacked. Well, how come? What changed? Was this system always hackable, or has it only become hackable recently, and what's happened? We're also seeing now more unusual systems under threat and being reported as being susceptible to vulnerability. So recently I've seen in the press some reports of SCADA systems. So this is the kind of industrial control systems, stuff that's running factories and so on, and chemical plants being susceptible to attack. So what's going on? How come these things are suddenly being reported over the last 5 years when they weren't perhaps so prevalent before? So what changed? Well, what changed mostly was the environment. The systems haven't changed. A lot of these systems have been out in the field for decades and they're fine, you know, in their original environment. What largely has changed is the environment. I did some reading around this subject and found this book by Gary McGraw called Software Security, Build Security, and it's a reasonably good book about the issues of how to build software that's reasonably robust in the face of this kind of problem. And in this book, in the introduction of the first few chapters, Gary identifies 3 things, or 3 particular changes in the environment which has caused this kind of problem. The first that he points out is basically everything's getting stuck on a network. If you want to make a system insecure, plug in the network cable on the back of it. And that's happened a lot in the last decade. We've gone from having systems which are isolated, doing particular jobs just fine. Someone comes along and says, hey, gee, wouldn't it be great to network all these computers together so that we can control them remotely or monitor them remotely, connect them all up to some network? So a picture here of lots of cables, and perhaps more recently it's not even cables anymore. Lots of networking is now wireless. So how many of you have a car that has a wireless connection to the outside world? Some of you may have a car that has a wireless connection to the outside world and you don't even know that it's there. It's difficult to see these days. I mean, a mobile phone, the infrastructure you need to be on a 3G network is now so ubiquitous and so small, you may not even know whether a particular system is connected to an open network or not. So connectivity has changed the game significantly. If everything's networked, then it can be terribly, terribly easy to get all sorts of problems. Another thing that changed, about 1997, I remember working on a project, I think Neil was involved and some of my other colleagues. We went to a project and it was the first time I'd seen this amazing stuff called flash memory. And there was this hardware target and there was this flash on it. And gee, you could reprogram it really easily. It behaved like read-only memory in that it kept its stuff when you switched it off. But you could reprogram it really easily. You didn't have to go and, it wasn't painful. You didn't have to unsolder the stuff or whatever. And things like flash memory have caused significant benefits in the world. Undoubtedly, the ability to upgrade systems in the field is important. But it creates an engineering mindset which is perhaps not beneficial, where if everything's easy to upgrade, then, hey, we can ship anything we like earlier and we'll pitch, this sort of patch it later mentality comes to mind, where systems can be upgraded arbitrarily or extended and so on and so on and so on. And programming languages have gone in this way. So with programming languages, a lot of languages now are very dynamically extensible. We have dynamic loading in programming languages where you suddenly, the program is able to extend itself while it's running almost, or at least while it starts up. And this is fantastic for all sorts of reasons, but does create certain issues of things like security. So if you've downloaded a patch into your computer, well, where did it come from? Who vouched for its authenticity? Should you have installed it in the first place, and so on. Growth in complexity has undoubtedly occurred. Software just keeps getting bigger and bigger and bigger. This graphic comes from an account by John Cholinsky of the size of software in various aircraft or various generations of aircraft from Boeing and Airbus. You'll note the y-axis is logarithmic, so that's not a straight line. That's actually a fairly sharp curve going up between from the early Boeing aircraft and Airbus aircraft up to the modern systems like the 777 and the A380. I think the growth of software size and complexity in cars is even more dramatic. Stuart would probably be able to tell us more about what the growth curve's like in automobiles, but these days I hear people talking about tens, if not hundreds of millions of lines of code in a modern automobile. All of which, of course, is on a network inside the automobile, which has a USB port or some sort of port that you can plug into in the car. Most of your cars these days have a network connection somewhere that you can plug a laptop into. And you can do all sorts of interesting things. There's an university in America developed a system called CarShark. Shark as in the fish, one word, CarShark, if you search for it. CarShark's an amazing thing. It enabled a bunch of university researchers to drive a car by sitting in the passenger seat, typing at a laptop. They were able to drive the car and also do some worrying things like apply the brakes. They said they didn't test this. The university professors said they didn't test it themselves. Of course, they got a student to test it. They drove it. They found a nice safe runway somewhere, drove a car down a runway fairly fast, and with a laptop, the guy was able to basically type a command, press return, and apply the brakes in the car from that kind of control. So if you want to find out about that, the CarShark system is a very interesting example of how this kind of attack can be mounted against something like an automobile and it's the network in there. So complexity, more size means more bugs, basically. And if more bugs are there, there's more to exploit or more to go wrong, and so on and so on. And perhaps our maturity in software engineering at deploying a particular defect rate in software has not kept up. If we want to multiply the size of the software in the car by a factor of 10, what we'd like to do is do a factor of 10 better in terms of defect rate to keep the number of overall defects the same. And perhaps we haven't kept up. So that the growth of complexity is outstripping our ability to control the quality of these things. So what's the big difference between safety and security? There are some notable differences. The biggest, as I said, is the environment. Mostly in the past, most of the safety-related systems we built, at least we had some control over the environment or the system in which the software was sitting, and we could take engineering steps to control the environment, and maybe it wasn't networked, or at least if it wasn't a network, it was a network that we built and we controlled, so it was okay. Security-related systems, in the worst case, the complete opposite is true. We have to assume that the environment is openly malicious, meaning it will fail, it will go wrong in the worst possible way, at the worst possible time, and it's not just an accidental failure, it's a malicious, intelligent failure that's, somebody intelligent is trying to make your system fail or force it into a particular state. Ross Anderson at Cambridge and Roger Needham coined the phrase programming Satan's computer in one of the papers they wrote. So it's this idea that it's a malicious target, it's a malicious computer system. You can't trust that it will actually do anything you want in the worst case. So that's a rather different set of assumptions for the engineering of such things. Even worse, you could imagine saying, well, what we'll do is enumerate all the possible ways our system could be attacked, and we'll enumerate all the bugs that we don't want, and then we'll make sure we've addressed them all. Well, even that doesn't work in the worst case, because we have to worry about defects and attacks and threats that we don't even know exist yet. Or how can that be possible? How can you defend against something if you don't know what it is? This happened in the smart card industry in the late 90s, when we were working on the Maltos system. The smart card industry was in a fine state, thought everything was good. And then a researcher came along and invented a new type of attack against smart cards and microprocessors in general. This chap realised that if you attached a very sensitive ammeter to a smart card and then ran millions of test cases and measured what the ammeter showed you very, very carefully, and then did a lot of statistical analysis, you could deduce what was going on the smart card, and this became known as differential power analysis. Before that was known, well, how could you have defended against that? And it turned out a great many microprocessors of the day were susceptible to that kind of attack. And the engineers had to go back to the drawing board and redesign stuff to obfuscate the power consumption, for example, to prevent this kind of weird power-based observation attack. And similarly, attacks against timing of systems are well published now, where previously people just didn't know that kind of thing was possible. Claims based on we've tested it lots therefore don't really hold up. Saying you've tested it lots clearly can't cover the cases of, stuff we don't know about, because you can't have written test cases for cases that you don't know. So that doesn't get us very far. So that led us, I suppose, into the mode of saying, well, what about using formal methods and this idea of sound analysis in the engineering of such systems, which we had found worked pretty well in the safety world. In building systems like the Maltos CA, and subsequently we've done projects like Tokeneer. We've done some work on doing reference implementations of crypto algorithms, and some of our other customers using Spark are in this domain as well. Our colleagues from Secunet are here today. Folks from Rockwell Collins from the States aren't here, unfortunately, but they've been working in a similar environment building secure systems. So we found that the soundness property and the use of formal methods really does work, because it gives us a level of confidence that we've proved that something will always be okay, regardless of the state of the system or regardless of the input data. So it does seem there's really some value there. So we get some basic stuff from the use of this kind of verification. So just the absence of dumb bugs. If you look online, you'll find lots of guidance that says, gee, you shouldn't have buffer overflows in your software, you shouldn't divide by zero, you should check your input data, you should validate inputs. Before you go off and query a database, you should check that what you were querying really was what you thought you should be looking at, all this kind of stuff. There's lots and lots of guidance. So the absence of these dumb bugs, and that's pretty basic stuff. That's stuff that we probably took care of in the early 1990s in the design of the Spark system. We just made it impossible for many of those bugs to appear in software, and we've been doing that ever since. So that's easy. More interesting is things like verifying specific properties. If you've got a formal specification of a safety property or some sort of security property, if that can be expressed in a program as an assertion, then we can use the verification technology to check that. So you may want to, express some invariant that something good always happens, or something bad can never happen, or whatever you might like. And we've done that to some extent with some systems like Sholis and Tokeneer, where we've managed to go as far as formally proving that certain things are true always relative to a particular set of assumptions. So we can do some stuff there. There's still no silver bullet though. We can have a marvellous verification technology to verify that we've remembered to validate our input data, but it won't tell you what valid is or isn't. You still have to have a policy, or you have to have some requirements to actually say, well, a valid query on this database must be as follows, dum 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 dum. It doesn't, get you out, I suppose. There's no free lunch with getting out of actually having to define that stuff properly. But at least if we have defined it properly, we can then go on to verify it, you know, down to the implementation. Some trends that we've observed. In the last 5 years, there's been an enormous resurgence of interest in the application of so-called static analysis, or what we might prefer to call static verification in software, the kind of stuff that we've been doing for many years. Now there are lots and lots of very interesting, very powerful tools out there that do this kind of stuff, mostly targeting what we would call the retrospective market, meaning if you've got a large code base of existing code, can you run a tool on it that will find some of the bugs? And there's a very active, well-developed market for such technology now. And given Moore's law, you know, the advance in computing power that we can put on our desktops, what's achievable now is staggering in comparison with what's achievable 5 or 10 years ago. There's been a huge resurgence. So that's a good thing. It raises people's awareness that this stuff is possible at all. It makes us feel good that we were sort of on the right track all along with sort of promoting this kind of technology, and certainly brings the average up from pretty low to a bit less low, perhaps. But what about the high end? What we'd like to do is actually look further than that. So a concern I have, perhaps, is that most of the energy we've seen in the last 5 to 10 years has been targeted at what in the States they particularly call the low-hanging fruit. So the low-hanging fruit is the millions of lines of code out there that nobody's really looked at before, and you want to find some of the buffer overflows or some of the bugs. That's fine, it certainly helps, but it does tend to give the impression that that's the best you can do, and we know that's not right. We know we can do a lot better than that. There tends to be also a trend or a fashion for so-called, what I would call enumeration of vulnerabilities. There's lots and lots of effort gone into making lists of bugs. If you go out on the web, you'll find lots of books or websites or papers and efforts where you'll find, for example, the SANS, you know, the top 25 software defects. There's a thing called the Common Vulnerability Enumeration, the Common Weakness Enumeration. There's an ISO group looking at programming language vulnerabilities and so on. And there's a lot of, it's very attractive to say, well, let's make a list of all the top things, all the things you shouldn't have in your software. And then if we tick them all off, surely that'll be all right then. And that's perhaps not the case. It's good as a starting point, but it's certainly not a be-all and end-all. And it does encourage a box-ticking mentality to software development, where you say, well, if I take care of these top 20 bugs, you know, is that good enough? The problem, of course, is that a really determined security attacker will always find the 21st bug, the one that you didn't tick. There'll always be one more bug that will be exploitable. And another concern there is that actually, when you get rid of all the dumb bugs, the easy ones, the ones you can enumerate tend to be the easy bugs that are just the simple stuff. Actually, what's really interesting is the application-specific and the domain-specific properties that we're interested in. So in the tokeneer system, there's a security property that says, I think it says, when the door is open and the guard is present, then the alarm may not be ringing. Okay? Now, that security property is not a bug or a vulnerability of a programming language or an operating system or something. You know, that's a property of the world that we wish to preserve. So you won't find that on a list of security bugs you should look for. That kind of property is where the fun starts. That's where the actual real value is. But those kinds of properties are enumerable. They're the properties of your system, systems that we haven't even built yet. So there's no list of them, or at least if you did try to make that list, you'd be making it for a very, very long time. So I'm worried about things like SQL injection as a sort of general vulnerability description. SQL injection is really saying, go away and write some requirements for what constitutes a valid SQL query. Well, that's up to you. And again, you can't really enumerate that in a simple way. So based on those observations, things are not perhaps as simple as we would like. We've certainly shown that the formal method stuff, the use of what we've called correctness by construction, at the implementation level, the use of Spark or similar technologies, can certainly yield strong results. We've seen that with systems like Tokeneer, Multos and Skein and work done with some of our customers, particularly at the higher grade level, so where we're interested in processing top secret data, data that needs to be very strongly protected. We've certainly seen the value in those approaches. But the world is more complex than that. We certainly see systems now that incorporate large code bases that come from a variety of sources. I guess some stuff you might call legacy code, some off-the-shelf components, off-the-shelf operating systems, libraries, goodness knows what. SOUP, in quotes, that's software of uncertain pedigree, for those of you not familiar with the term. This is a catch-all used for stuff that we don't know where it came from, or something like that. This stuff tends to be written in many languages, programming languages of all sorts, possibly by many teams, possibly in many countries. You know, in large systems, people do worry a great deal about the supply chain for such systems. Where has this stuff all even come from? Can you identify who wrote it? It's a serious problem with some of the larger systems we see. Secondly, the boundary between safety and security is becoming blurred. The more and more systems we network together, well, are systems all safety related, or are they security related? And it appears the answer is, well, both. Or more and more these days we're seeing such properties, such systems exhibit both properties. It was interesting last night over dinner, I think Robert from SecuNet pointed out that in German there's only one word for both these concepts. I think English is problematic in this sense, in that we have these two words, so people get this idea that it's two different concepts, and perhaps it isn't. In German, it's just the one word. Can anyone remind me what the word is, Robert? Sicherheit. It's Sicherheit in German, and it encompasses both of these concepts. So we're moving to an area where we want to be able to build systems that exhibit both safety and security properties. It would be nice to be able to build those systems without having to spend twice as much money. It would be nice to be able to reuse the evidence that we get, or the engineering, to actually achieve both goals as well. So where might we be in future? Clearly architecture is important. It's not just about programming languages and software and verification tools and stuff. Architecture is probably the principal weapon that we've always had and will continue to have for building such systems. So in the old days there was an easy architectural choice. If you had a system that processed top secret data and a system that processed unclassified data, well, they were just different systems. They were different boxes, sat on different networks. You know, one was red and one was black or something, and the network cables were different colours. And they were literally just physically separate. That's one possibility, and indeed many systems are built that way. But these days, we need to be able to mix these systems, have them running on the same box. So, for example, the demo that SecuNet have brought today is an example of such a system that's able to deal with multiple classifications on the same physical hardware. Even that's becoming difficult, though. Just recently there was an attack published where some researchers demonstrated a attack where one virtual machine running on a piece of hardware was able to observe the behaviour of a different virtual machine running on the same hardware, and that's not supposed to be possible. It's the kind of thing that the operating system vendors will tell you, oh yeah, this is great because these virtual machines are separate and they can't interfere with one another. Well, somebody recently, you know, has demonstrated a cryptographic attack between two distinct virtual machines on the same box. So even with architectural mechanisms like virtualization and separation kernels, it's not as simple as you might think. What else can we do? So we've got the formal method stuff, and that's great. But what about other systems which aren't amenable to the formal analysis? Can we talk about testing those systems or isolating them in a way which is appropriate to contain them or whatever, to get the techniques, to get the properties that we want? And maybe just keep the formal method stuff for hopefully the smallest, most high integrity component, and architect the system to exhibit that behaviour. Contractualization is a very interesting idea. What we'd like to be able to do is certainly at the boundaries of systems to be able to make contracts. And a contract could be a legal thing between you and a supplier, or internally within a piece of software. A contract is something that says at the boundary of a piece of software, I'm a unit and I promise to do X and I promise not to do anything else, or something like that. If we can make such contracts strong enough and enforce them properly, can we then begin to be able to trust the interface between two subsystems or two components of the software system? So contractual enforcement is very interesting, and I know it's something that Cyril's going to mention. How can we move from the formal world on one side to a world perhaps where we're testing and isolating on the other side of a contract in a more dynamic, a more flexible way than having to just do the formal methods on everything? So, with those things in mind, there's issues there, you know, and I'm not saying we know how to do all of this, we certainly don't. But there's certainly an approach needed where I think we need to recognise the need to be able to combine systems which are formally developed with systems which are off the shelf, systems which are legacy and yet trusted through their history or use, and perhaps systems of lower integrity which we're willing to perhaps not be so formal with. So in that regard, I think, at this point, I'll take a couple of questions or observations from the audience, but then I'd like to hand over to Cyril, who is going to expand on this idea of how we can combine these sources of evidence from different verification techniques.